The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let's start right away with stuff that we will need to see before we can go on to more advanced things. So hopefully yesterday in recitation you heard a bit about vectors. How many of you actually knew about vectors before that? Okay, that's the vast majority. If you're not one of those people, well, hopefully you will learn about vectors right now. I'm sorry that the learning curve will be a bit steeper for the first week, but hopefully you will adjust fine. If you have, trouble with vectors, do go to your instructors, recitation instructors' office hours for, extra practice if you feel the need to. You'll see it's pretty easy. So, just to remind you, a vector is a quantity that has both a direction and a magnitude or length. So concretely, the way you draw a vector is by some arrow like that, okay? And so it has a length, and it's pointing in some direction. And so now the way that we compute things with vectors typically is we introduce a coordinate system. So if we're in the plane x, y axis, if we're in space x, y, z axis, so usually I will try to draw my x, y, z axis consistently to look like this. And then I can represent my vector in terms of its components along the coordinate axis. So that means when I have this arrow, I can ask how much does it go in the x direction, how much does it go in the y direction, how much does it go in the z direction. And so, for example, let's call this vector A. So a small convention. When we have a vector quantity, we put an arrow on top to remind us that it's a vector. If it's in a textbook, then sometimes it's in bold because it's easier to typeset. If you've tried, in your favorite word processor, there's bold is easy and vectors are not easy. So the vector, you can try to decompose in terms of unit vectors directed along the coordinate axis. So the convention is there's a vector that we call I hat that points along the x-axis and has length 1. There's a vector called j hat that does the same along the y-axis, and a k hat that does the same along the z-axis. And so we can express any vector in terms of its components. So the other notation is a1, a2, a3 between these square brackets. Well, maybe I should say angular brackets. So the length of a vector we denote by, if you want, it's the same notation as the absolute value. So that's going to be a number. Or as we say now, a scalar quantity. Okay, so a scalar quantity is a usual numerical quantity as opposed to a vector quantity. And its direction is sometimes called dir of A, and that can be obtained just by scaling the vector down to unit length. For example, by dividing it by its length. Okay. So well, there's a lot of notation to be learned. So for example, if I have 2 points, P and Q, then I can draw a vector from P to Q, and that vector is called vector PQ. Okay? So maybe we'll call it A. But a vector doesn't really have necessarily a starting point and an ending point. Okay? So if I decide to start here, and I go by the same distance in the same direction, this is also the vector A. It's the same vector. So a lot of vectors will draw starting at the origin, but we don't have to. Okay? So let's just check and see how things went in recitation. Where did I put it? So let's say that I give you the vector 3, 2, 1. And so what do you think about the length of this vector? Okay. I see an answer forming. So a lot of you are answering the same thing. Maybe I shouldn't spoil it for those who haven't done it yet. Okay, I think the overwhelming vote is in favor of answer number 2. I see some 6s. I don't know. That's a perfectly good answer too. But hopefully, in a few minutes, it won't be I don't know anymore. So let's see. How do we find the length of a vector 3, 2, 1? Well, so this vector A, it comes towards us along the x-axis by 3 units. It goes to the right along the y-axis by 2 units. And then it goes up by 1 unit along the z-axis. Okay, so it's pointing towards here. That's pretty hard to draw. So how do we get its length? Well, maybe we can start with something easier, the length of a vector in the plane. So observe that A is obtained from a vector B in the plane. Let's say B equals 3i hat plus 2j hat. And then we just have to still go up by 1 unit. Okay? So let me try to draw a picture in this vertical plane that contains A and B. If I draw it in the vertical plane, so that's the z-axis, that's not any particular axis, then my vector B will go here, and my vector A will go above it, and here that's 1 unit. And here I have a right angle. So I can use the Pythagorean theorem to find that length A squared equals length B squared plus 1. Now, we are reduced to finding the length of B. But the length of B we can again find using the Pythagorean theorem in the xy plane, because here we have a right angle. Here we have 3 units, and here we have 2 units. Okay, so if you do the calculations, you will see that, well, length of B is square root of 3 squared plus 2 squared, that's 13, so square root of 13. And length of A is square root of length B squared plus 1 squared, if you want, which is going to be square root of 13 plus 1 is square root of 14. Hence, answer number 2, which almost all of you gave. Okay, so the general formula, if you follow what we did, in general, if we have a vector with components A1, A2, A3, then the length of A is the square root of A1 squared plus A2 squared plus A3 squared. Okay, any questions about that? Yes?
Does this pattern continue for values above A3?
Yes, so in general, we indeed can consider vectors in abstract spaces that have any number of coordinates, and then you have more components. In this class, we'll mostly see vectors with 2 or 3 components only, because they're easier to draw, and because a lot of the math that we'll see works exactly the same way, whether you have 3 variables or a million variables. If we had a vector with more components, then we would have a lot of trouble drawing it, but we could still define its length in the same way by summing the squares of the components. So I'm sorry to say that here, multivariable, multi will mean mostly 2 or 3. But be assured that it works just the same way if you have 10,000 variables. Just calculations are longer. Okay. More questions? No? Okay. So what else can we do with vectors? Well, another thing that I'm sure you know how to do with vectors is to add them or to scale them. So vector addition. So if you have 2 vectors, A and B, then you can form their sum A plus B. How do we do that? Well, first, I should tell you, vectors, they have this double life. They're at the same time geometric objects that we can draw like this on pictures, and they are also computational objects that we can represent by numbers. So every question about vectors will have 2 answers, one geometric and one numerical. Okay, so let's start with the geometry. So let's say that I have 2 vectors, A and B, given to me. And let's say that I thought of drawing them at the same place to start with. Well, to take their sum, what I should do is actually move B so that it starts at the end of A, at the head of A. Okay, so this is again vector B. So observe, this actually forms now a parallelogram, right? So this side is again vector A. And now, if we take the diagonal of that parallelogram, this is what we call A plus B. Okay, so the idea being that to move along A plus B, it's the same as to move first along A and then along B. Or along B, then along A. A plus B equals B plus A. Okay, now if we do it numerically, then all you do is you just add the first component of A with the first component of B, the second with the second, and the third with the third. Okay, say that A was A1, A2, A3, B was B1, B2, B3, then you just add this way. Okay, so it's pretty straightforward. So, for example, I said that my vector over there, its components are 3, 2, 1, but I also wrote it as 3 times I plus 2 times j plus k. What does that mean? Oh, so I need to tell you first about multiplying by a scalar. So maybe I should say this is about addition. So multiplication by a scalar, it's very easy. If you have a vector A, then you can form a vector 2A just by making it go twice as far in the same direction. Okay? Or we can make half A more modestly. Or we can even make minus A, and so on. Okay? So now you see if I do the calculation 3 times I plus 2 times j plus k, well, what does it mean? 3 times I is just going to go along the x-axis, but by distance of 3 instead of 1. And then 2 times j goes 2 units along the y-axis, and k goes up by 1 unit. Well, if you add these together, you will go from the origin, then along the x-axis, then parallel to the y-axis, and then up. And you will end up, indeed, at the end point of the vector A. OK. Any questions at this point? Yes?
So for the geometric vector addition, you're basically just using the tip-to-tail addition?
Exactly. To add vectors geometrically, you just put the head of the first vector and the tail of the second vector in the same place, and then it's head-to-tail addition. Any other questions? Yes?
So when you're subtracting, you just flip one in another direction?
That's correct. If you subtract 2 vectors, that just means you add the opposite of a vector. So for example, if I wanted to do A minus B, I would first go along A and then along minus B, which would take me somewhere over there. OK? So A minus B, if you want, would go from here to here. Okay. So, well, hopefully you've kind of seen that stuff either before in your lives or at least yesterday. So I'm going to use that as an excuse to move quickly forward. But so now we're going to learn a few more operations about vectors. And these operations will be useful to us when we start trying to do a bit of geometry. So of course, you've all done some geometry, but we're going to see that geometry can be done using vectors. And actually, in many ways, it's the right language for that. And in particular, when we learn about functions, we really will want to use vectors more than maybe the other kind of geometry that you've seen before. I mean, of course, it's just a language in a way. I mean, we're just reformulating things that you have seen, you already know since childhood. But you'll see that the notation somehow helps to make it maybe more straightforward. So what is dot product? Well, dot product is a way of multiplying two vectors to get a number, a scalar. And, well, let me start by giving you a definition in terms of components. So what we do, let's say that we have a vector A with components A1, A2, A3, a vector B with components B1, B2, B3. Well, we multiply the first component by the first component, the second by the second, the third by the third. If you have n components, you keep going, and you sum all of these together. Okay, and important, this is a scalar. Okay, you do not get a vector, you get a number. I know it sounds completely obvious from the definition here, but in the middle of action, when you're going to do complicated problems, it's sometimes easy to forget. So that's a definition. What is it good for? Why would we ever want to do that? That's kind of a strange operation. So probably to see what it's good for, I should first tell you what it does geometrically. Okay, so what does it do geometrically? Well, what you do when you multiply two vectors in this way, I claim the answer is equal to the length of A times the length of B times the cosine of the angle between them. So if I have my vector A, and if I have my vector B, and I have some angle between them, I multiply the length of A times the length of B times the cosine of that angle. So that looks like a very artificial operation. I mean, why would we want to do that complicated multiplication? Well, the basic answer is it tells us at the same time about lengths and about angles. And the extra bonus thing is that it's very easy to compute. If you have a component, see, that formula is actually pretty easy. So, okay, maybe I should first tell you, how do we get this from that? Because in math, one tries to justify everything to prove theorems. So if you want, that's a theorem. That's the first theorem in 1802. So how do we prove that theorem? How do we check that this is indeed correct using this definition? So, or in more common language, what does this geometric definition mean? Well, the first thing it means, before we multiply two vectors, let's start multiplying a vector with itself. That's probably easier. So if we multiply a vector A with itself using this dot product, so by the way, I should point out we put this dot here, that's why it's called a dot product. So what this tells us is we should get the same thing as multiplying the length of A with itself, so squared, times the cosine of the angle, but now the cosine of an angle of 0, cosine of 0, you all know is 1. Okay? So that's going to be length A squared. Well, does that stand a chance of being true? Well, let's see. if we do a dot a using this formula, we will get a1 squared plus a2 squared plus a3 squared. That is indeed the square of the length. So check. That works. Okay? Now, what about two different vectors? Can we understand what this says and how it relates to that? So let's say that I have two different vectors, A and B, and I want to try to understand what's going on. So my claim is that we are going to be able to understand the relation between this and that in terms of the law of cosines. So the law of cosines is something that tells you about the length of the third side in a triangle like this in terms of these two sides and the angle here. Okay, so the law of cosines, which hopefully you have seen before, says that, so let me give a name to this side. Let's call this side C, and as a vector, C is A minus B. It's minus B plus A. So it's getting a bit cluttered here. So the law of cosines says that the length of the third side in this triangle is equal to length A squared plus length B squared. Well, if I stopped here, that would be Pythagoras, but I don't have a right angle. So I have a third term, which is twice length A, length B, cosine theta. Okay? Has everyone seen this formula sometime? Yeah, no. I hear some yes, I hear some no's. Well, it's a fact about, I mean, you probably haven't seen it with vectors, but it's a fact about the side lengths in a triangle. And, well, I'm not sure that well, let's say if you haven't seen it before, then this is going to be a proof of the law of cosines, if you believe this. Otherwise, it's the other way around. So let's try to see how this relates to what I'm saying about the dot product. So I've been saying that length C squared, that's the same thing as C dot C. Okay? That we have checked. Now, C dot C, well, C is A minus B. So it's A minus B, dot product A minus B. What do we want to do in a situation like that? Well, we want to expand this into a sum of 4 terms. Are we allowed to do that? Well, you know, we have this dot product. It's a mysterious new operation. We don't really know. Well, the answer is yes, we can do it. You can check from this definition that it behaves in the usual way in terms of expanding, factoring, and so on. So I can write that as A dot A minus A dot B minus B dot A plus B dot B. Okay. So A dot A is length A squared. Let me jump ahead to the last term. B dot B is length B squared. And then these two terms, well, they're the same. You can check from the definition that A dot B or B dot A are the same thing. So there's no hidden trick here. This is really minus twice A dot B. Okay? So now let's compare these two formulas. Well, you see that this term is, I mean, this is the only difference between these two formulas for the length of C. So if you believe in the law of cosines, then it tells you that, yes, this is a proof that A dot B equals length A, length B, cosine theta. Or vice versa, if you've never seen the law of cosines, but you're willing to believe this, then this is the proof of the law of cosines. Okay, so the law of cosines or this interpretation are equivalent to each other. Okay, any questions? Yes?
Why isn't there cosine theta in the second one?
So in the second one, there isn't a cosine theta because I'm just expanding a dot product. Okay, so I'm just writing C equals A minus B, and then I'm expanding this algebraically, and then I get to an answer that has an A dot B. So then if I wanted to express that without a dot product, then I would have to introduce a cosine, and I would get the same as there. Okay? So yeah, if you want, the next step to recover the law of cosines would be to plug in this formula for A dot B, and then you would have a cosine. Okay, let's keep going. Okay, so what is this good for? Now that we have a definition, we should figure out what we can do with it. So what are the applications of dot product? Well, we'll discover new applications of dot product throughout the entire semester, but let me tell you at least about those that are readily visible. So one is to compute lengths and angles, especially angles. So let's do an example. Let's say that, for example, I have in space, I have a point P, which is at 1, 0, 0. I have a point Q, which is at 0, 1, 0. So it's at distance 1 here, 1 here. And I have a third point R at 0, 0, 2. So it's at height 2. And let's say that I'm curious and I'm wondering what is the angle. So here I have a triangle in space connecting P, Q, and R. And I'm wondering what is this angle here. Okay? So of course, one solution is to build a model and then go and measure the angle. But we can do better than that. We can just find the angle using dot product. So how would we do that? Well, so if we look at this formula, we see, so let's say that we want to find the angle here. Well, let's look at the formula for PQ dot PR. Well, we said it should be length PQ times length PR times the cosine of the angle. Okay? Now, what do we know and what do we not know? Well, certainly at this point, we don't know the cosine of the angle. That's what we would like to find. But the lengths, certainly we can compute. We know how to find these lengths. And this dot product we know how to compute because we have an easy formula here. Okay, so we can compute everything else and then find theta. So actually what we will do is we will find theta in this way. We'll take the dot product of PQ with PR, and then we'll divide by the lengths. Okay, so let's see. So we said cosine theta is PQ dot PR over length PQ, length PR. So let's try to figure out what is vector PQ. Well, to go from P to Q, I should go -1 unit along the x direction, +1 unit along the y direction, and I'm not moving in the z direction. So to go from P to Q, I have to move by -1, 1, 0. To go from P to R, I go -1 along the x-axis and +2 along the z-axis. So PR, I claim, is this. Okay? Then the lengths of these vectors, well, we take -1 squared plus 1 squared plus 0 squared, square root, and then same thing with the other one. Okay? So the denominator will become, well, there's a square root of 2, and there's a square root of 5. What about the numerator? Well, so remember, to do the dot product, we multiply this by this, then that by that, that by that, and we add. -1 times -1 makes 1. Plus 1 times 0, that's 0. 0 times 2 is 0 again. So we will get 1 over square root of 10. Okay? That's the cosine of the angle. And of course, if we want the actual angle, well, we have to take a calculator, find the inverse cosine, and you'll find that it's about 71.5 degrees. Actually, we'll be using mostly radians, but for today, I mean, that's certainly a more speaking answer. Okay, any questions about that? No? Okay, so in particular, I should point out one thing that's really neat about the answer. See, I mean, we got this number. We don't really know what it means exactly because it mixes together the length and the angle. But one thing's interesting here, it's the sign of the answer. The fact that we got a positive number. So if you think about it, the lengths are always positive. So the sign of the dot product is the same as the sign of cosine theta. So in fact, the sign of A dot B is going to be positive if the angle is less than 90 degrees. So that means geometrically, my two vectors are going more or less in the same direction. They make an acute angle. It's going to be 0 if the angle is exactly 90 degrees. Okay? Because that's when the cosine will be 0. And it will be negative if the angle is more than 90 degrees. So that means they go rather in opposite directions. Okay, so that's basically one way to think about what dot product measures. It measures how much the two vectors are going along each other. Okay. And that actually leads us to the next application. So let's see, did I have a number 1 there? Yes, so if I had a number 1, I must have a number 2. The second application is to detect orthogonality. It's to figure out when two things are perpendicular. Okay, so orthogonality is just a complicated word from Greek to say things are perpendicular. So let's just take an example. Let's say I give you the equation x plus 2y plus 3z equals 0. Okay? So that defines a certain number, a certain set of points in space. And what do you think the set of solutions looks like if I give you this equation? So far I see 1, 2, 3 answers. Okay. So I see various competing answers, but yeah, I see a lot of people voting for answer number 4. I see also some I don't knows and some other things, but the majority vote seems to be a plane. And indeed, that's the correct answer. So how do we see that it's a plane? So I should say this is the equation of a plane. So there's many ways to see that. And I'm not going to give you all of them, But here's one way to think about it. So let's think geometrically about how to express this condition in terms of vectors. So let's take the origin, O by convention is the point 0, 0, 0. And let's take a point P that will satisfy this equation or not. So at coordinates x, y, z. So what does this condition here mean? Well, it means the following thing. So let's take the vector OP. Okay, so vector OP, of course, has components x, y, z. Now, we can think of this as actually a dot product between OP and a mysterious vector that won't remain mysterious for very long, namely the vector 1, 2, 3. Okay, so this condition is the same as OP dot A equals 0. Right? If I take the dot product OP dot A, I get x times 1 plus y times 2 plus z times 3. But now, what does it mean that the dot product between OP and A is 0? Well, it means that OP and A are perpendicular. Okay? So I have this vector A. I'm not going to bother to draw it realistically. Let's say it goes, for example, this way. Then a point P solves this equation exactly when the vector from O to P is perpendicular to A. And I claim that defines a plane. For example, if it helps you to see it, take a vertical vector. What does it mean to be perpendicular to the vertical vector? It means you're horizontal. It's the horizontal plane. Here, it's a plane that passes through the origin and is perpendicular to this vector A. Okay, so what we get is a plane through the origin, perpendicular to this guy A. And in general, what you should remember is that two vectors have a dot product equal to 0 if and only if that's equivalent to cosine of the angle between them is 0. That means the angle is 90 degrees. That means A and B are perpendicular. So we have a very fast way of checking whether two vectors are perpendicular. Okay. So one additional application, I think we'll see that actually tomorrow, is to find the components of a vector along a certain direction. So I claim we can use this intuition I gave about dot product telling us how much two vectors go in the same direction to actually give a precise meaning to the notion of component of a vector, not just along the x, y, or z axis, but along any direction in space. So I think I should probably stop here. But I will see you tomorrow at 2 here. And we'll learn more about that and about cross product.